Thanks. So last time we finished the discussion about the dead code elimination, and I hope you had a little bit of a break because of the yesterday's holiday. Just a quick announcement: next Wednesday there's another scheduled holiday, which happens to be the day of our class. So we won't have a class on that particular day, next Wednesday, but we'll of course have a class on Monday. And the homework is due, I think, on Tuesday. So what I'm going to do today is very briefly, as I mentioned last time, give a brief overview of the SCCP and let you read and answer the homework questions and read the Mutinic handout and so on. And then move on to the big optimization that we have SSA for, which unifies a lot of other stuff also, which is global value numbering, and that will be the last optimization we'll talk about using SSA, and then we'll move on to the other topics. So today and Monday we'll cover global value numbering mostly, value numbering, and then followed by global value numbering. So let me get set up here for SCCP. And we'll go from there. Okay, SCCP. See if we can. Oops. It's on the SCCP window. Should go for. Okay. I hope you're seeing the SCCP. Can you?
Yes, we can see it.
Okay. Is it showing that window? That's not the one I wanted to. Sorry, 1 minute. Okay, now it should be good. Let's see if we can get hold of that window. All right, this is the right one, because this is so constant propagation on SSA form, which is also called as sparse conditional constant propagation. And typically, again, what happens is the normal constant propagation doesn't work because of limitation, of course, of a join of a constant and a non-constant value, and there happens to be an opportunity, especially inside again loops, where it really matters a lot to be able to get more constants picked up than otherwise. And however, that needs much more detailed analysis, which is much more than what we call as a summary analysis of a program. So what is a summary analysis? Summary analysis is what we have seen in the traditional data flow. We typically break things down into basic blocks, and then we start analyzing and propagating the properties at the entrance and exit and through the block. And we summarize the reaching definitions, and we summarize the sort of available expressions, etc., at the respective basic block boundaries. And then we use the results of that to carry out the optimization. So you can see that the analysis is summarizing information at the boundaries. And per se, we don't need to really propagate the information along the different statements of the program and so on to be able to do some optimizations. But that's not the case with the sparse conditional constant propagation and the previous analysis that we also saw, the dead code elimination. You could see there that we had to go through pretty much every statement of the program, worst case, and mark it, and that costs a lot of time. So unless we have a very fast mechanism to go from one statement to the other, it is going to be expensive affair, and that's where the SSA's main role is. As we saw in the dead code elimination, we are able to generate the relevant data flow and also control dependencies for each statement. We got to go through each statement in the worst case, because if each statement is sort of relevant to the critical value or output value, then we have no choice except to go through it. So roughly the order of complexity is the length of the program that we are talking about. And then at each step, however, if we pay a lot of overhead or a lot of time, then it's going to be very expensive. And so the SSA allows us to go from one statement to the relevant statement very quickly in a constant time. We don't have to do extra analysis to determine this relationship, because that's what we call as SSA edges. And exactly that is what is relevant here. So what we do here in this analysis roughly is try to get the constant propagated and also evaluate the different branch conditions and things like that if they're relevant. That leads us to more precise analysis, wherein we find more constants, and it doesn't cost because it's very fast. So what we do here in this particular analysis, roughly to sort of give you an idea, is to evaluate something in a different way, in what we call as an optimistic manner. What we do to begin with is initial expressions in terms of three values they could generate. So there is something called as a value, which is, let's look at the simple classification first. A variable value of a particular, so let's look at the L value of a statement, of a particular IR statement. If it is known to vary, it is called as bottom in the lattice terms, and some of you might have studied lattices in mathematics, know this particular term, but don't. This is so some variable which we read from, for example, from an input, and the user could just send in any value that we don't know about, and it could vary at runtime depending on what the user says. That's a value which is known to vary, and it is called as bottom. Now, for some other statements, so like read statement and all, which reads things from keyboard, such values could be bottom, which are known to vary. Now, the other value that could be associated with a statement is our well-known constant. For example, a is equal to 10. So the L value of a here is known to be a constant. So again, it is known, but it's known to be a constant and not a variable. So that's the second classification of a value. And then the third value, let's say something like k is equal to d. We don't know what's going on with d here, whether it is really a constant, whether it is really a variable. So at this point, we will classify it as something unknown or a top. And the same thing happens to be true about even phi functions. So phi functions have different values coming in. If you can see on the box on the right hand side down here, the phi function's output value could be one of the x1s through xn, correct? We don't know, for example, this particular phi function, whether they are all the same constants or whether they are different constants or whether one of them is a variable and one other is a constant. So at this particular point, we don't know which way this function will really evaluate. So we brand it as a top. Okay. So one which is unknown is top. One which is known is and constant is some constant value, and that Ci is the value of that thing. And the one which is known to vary is bottom. Now, what we want to do here is this, that we want to evaluate the values of all the IR statements given this initial assignment, and propagate the constants, of course. And wherever we face unknowns, we will evaluate it in a given way. And that lattice is the critical one, which is going to tell us what is the final outcome of this evaluation. So typically what we want to do is take all the unknowns. So whatever is known, maybe it is a constant, whatever is a varying one, we don't care about it. We, of course, let's settle down in their final values. Whatever is being read from the keyboard is going to vary. There's no way it will be all the time constant because the user is definitely guaranteed to type the same number like 10 all the time. So that is settled. Whatever is known is settled in a constant or a varying one. But whatever is unknown, which is a top, which is to be resolved. So what we want to do this in this particular case is we want to evaluate this. The whole goal of this is to be able to evaluate this particular unknowns and resolve them into knowns. So without getting into the too much details of how this happens through this particular loop, which you will quickly understand, let us look at what the issues are here in terms of resolution of these unknowns. The currently the pessimistic way of dealing with this particular lattice is this, that suppose if you're dealing with let's say one of these x1 values, again focus on this small blue box here. If one of them is constant, let's say x1 is a constant definition, we know that it's a constant. But the other ones are unknowns, that is, they are all tops. Then then you can say that as per the proper original definition of the lattice is that we will evaluate this to as something which is which will keep it as an unknown, as a top, or we'll make an assumption that one of the values could be varying and is bottom, and we'll use that to say that the phi is in fact a bottom. But of course, what if this value itself that is participating in this phi function is not really reaching here, in the sense of, if we evaluate the constant, propagate it, and evaluate a branch, and so on, if that generates a value which never reaches here, then our assumption is wrong. And that is where the lattice modeling happens to make a difference. So let's look at what is going on here. This particular example will clarify it. We have this I0 as a constant. We have a while loop. Obviously, there is in the SSA function here is this I0 is coming in from the top as one of the arguments to this phi function. And the second argument is I3, which is a loop originated definition of I. And in between, what is going on is this I1 is generated, of course, in the SSA form. It participates in this X being I1 times 17. And then this I1 goes to J, and some other J2 generates there, so I2 generates there. And I3 goes back to J. So if you really carefully trace the flow of data flow of I here, see what is going on. I0 is coming in. Of course, the phi function will evaluate to I0 the first time. I1 will get I0 value, and then J will get again I0 value, and then I3 will become equal to I0. So all the time you'll see that even I3 will stay on the I0 front here, and the values of i's that are seen all through and through will always be 12. And however, if we use the SSA formula, the constant propagation, which is our current propagation, you will see that the I3, which is not declared a constant here, will join with I0, which is a constant, and therefore make I2 as a non-constant, and similarly, I1 as a non-constant, and J as a non-constant, and so on. So because of this way of propagating constant, which are just purely based on whether the originating definition is a constant or not, the transitive effects of these constants are not really taken into consideration. And if we use the bottom lattice to model this phi function here, we cannot really use, we cannot really get this constant propagated. So in other words, if we treat the phi function and I3 as unknown or a bottom, which is what we do in the traditional analysis, bottom merging with constant produce a bottom and I1, and reinforce the bottom and back in I3, and that will evaluate to a pessimistic solution in which the constant will not get detected. So the optimism is what really pays off here. So instead of initializing everything to the bottom, we initialize everything to the top, which is unknown, which is the case actually. And when the top is then, so I3 will be modeled as a top here, not as a bottom. So in the previous version, I3 will be varying because its right-hand side is varying, and so on. And in reality, of course, it's not varying. It's really a constant because it's really same as I0. So, but conservatively, if we model it as a bottom, then the bottom will get married with the constant at the phi function and will produce a bottom which will propagate through and through and will lead to a non-constant. So instead of modeling now all the values which are unknown, which instead of calling them conservatively as bottom, if we call them as unknown, which is a top, let us see how this things first functions. So this was the data flow I was talking about, So that leads to this constant. So let us see how this original pessimistic evaluation goes. So when we evaluate um, um, everything as initialized to the bottom, you can see that I3 flows from there to the phi function, and you'll see that I1 is now married with the bottom, produces bottom. X produces bottom in terms because of I1 going there, and J produces bottom as well because of I1, and then I2 is bottom initialized, and then I3 remains bottom. So this is the solution at the convergence of initialization of the unknowns as to be varying in a conservative sense. Whereas if you do this in a different way now, and this is the essence of sparse conditional constant propagation. We say that, hey, we have only two things right now. We don't have a bottom unless proved so, which basically means that it actually has to vary. And we have something which is a constant to begin with. And then whatever is unknown, we don't know anything about that. We just call it as a top. And then we model the lattice in terms of optimistic evaluation. So what is that optimistic evaluation? So let us look at right away. It is very clear here. I1 is evaluate. This is a phi function which is evaluating here, which is 12 coming from I0's value, which is a constant 12. And of course, it is married with the top because of I3. And here is what we say, that we optimistically assume that this top is somehow the same constant. Instead of the previous assumption that when we take this bottom and marry it with the 12, it remains something which is varying, which is known to vary, and it's not a constant. Here is when we marry an unknown with a constant, we say that, hey, optimistically that unknown, let's assume that it is a constant right now unless we prove it otherwise. And if we use this assumption, then you can see that I1 produces a constant first, and then X produces again a constant, whatever that is, and that's not relevant here per se. And then J produces constant because I1 is a constant. That is important. And then this J is propagated further in terms of I3, and that produces a constant. And when we propagate I3 back here onto the original phi function, that completes the iteration and terminates in terms of a fixed point here solution, which is really a constant. So the change of assumptions from unknown to a top, and the optimism that when we that the top will be mostly evaluated to a constant, helps this termination of things as a constant. And you can see that beautifully because of this reason, so many things inside the while loop are suddenly turned into constants, whereas they were all varying and they were non-constants in the previous things. Now, this particular thing has, of course, a lot of implication because this is a constant inside a loop which we get detected. And you can see here that there is a lot of propagation. From I0, we had to propagate its value to evaluate this phi function. Then from there, we have I1, and we had to go from I1's definition point to its use point to propagate that information, whether it is a bottom or a constant or a top, whatever that is. And so all this propagation is means in the worst case, walk through all the statements of the program. And again, in this particular case, it is the size of the program, the complexity, and that is facilitated by the SSA edges. So what is the SSA edge here? The SSA edge goes from the definition I0 to its use I0 in the phi function, and it propagates things from the definition to its use. And then once we know the value of I0, or we update it based on iteration and so on, we will propagate the new value to the phi function, and from there we'll propagate the new value of I1 to wherever it is used and so on. And that's how we will be abstractly, so to say, evaluate this program. Another caveat here is this implicitly, because this is an IR. This is not an IR, you don't see that, but we also do one other thing here. We evaluate a block only when it is enabled in terms of a control flow, not otherwise. So for example, once we evaluate I0 here, the first basic block, which is inside this while loop, is enabled because it's a fall through branch. It definitely will execute. And that particular way we'll be propagating this information in terms of its propagation in the sense of whatever has become executable is what we'll be doing. So the implementation of the algorithm has two parts. One is the SSA work list to keep track of which needs to be propagated and which is the next SSA statement which needs to be evaluated by propagating this information, just like I0's information was propagated to the phi function. That is one thing. And the second thing is to find out which blocks are become executable or reachable because of the branches or fall through things and so on. And by doing this particular propagation on both of them, and by using these optimistic things, we are able to get rid of we are able to sort of rather do a more aggressive propagation of constant. And again, this is the algorithm which does that. So I think the other parts of it should be very clear and apparent here. What we are trying to do here is keep track of the blocks which have been enabled there. The SSA propagation part is fairly straightforward. You can see it that the SSA work list, we are trying to propagate used things to V, and so let this be O operation, and T be the result of evaluating this particular thing. So we'll take that and we'll take the SSA edge, and then we will evaluate it based on things and put it on the work list and so on. So that's the one. But the other one, which is phi function, you can see that look at the left-hand side box. What it is there is if we reach a branch in this particular case, which will, because of the evaluating the basic block there, which is enabled for execution. So we'll walk through each statement in the basic block in the lexical order, eventually reach branch. And if the one of the arguments is bottom, then we know that it is known to vary. And obviously the outcome of that branch will also vary. So in that case, we'll put both targets of that branch on the CFG work list. So we'll evaluate both basic blocks again through this process. However, if the argument happens to evaluate to true using the SSA propagation, etc., then the true side of the target is put. Otherwise, the false side of the target is put. And if it's an unconditional branch, then obviously we just process it because it is always going to execute. And the way, I guess, things will work because of this. It will pick up unreachable code, and it will have a very nice way of keeping the constant as reinforcing the constant. So so you can see here in this particular case that if we assume all paths execute, then we get a different result here. So you can see that I-17, if we go to this block and that other basic block, and we assume that both of them could execute because of the original modeling of the problem, and don't account for this propagation using this algorithm, then we got to assume that we might have J as 10 or as 20, and that will mean that this J3 will become equal to a bottom, and J3 will not be a constant. In this particular case, you can see that both are bottoms. K will evaluate to a bottom and so on. However, now let's look at the SSA oriented version, and trying to mark something which is here is going to, along with the optimism, is going to really help out. So you can see here that if we propagate I into the branch predicate I greater than 0, the branch does evaluate to true, and it never evaluates to false. It means J1 will become a constant there. And as a result of this, the optimistic lattice top being married to a constant now, you can see J3 will evaluate to be 10, and then eventually K will be 170. Other techniques cannot get to it, like dead code elimination, etc., because they are all useful as far as the output is concerned, and they will not be able to get rid of such things. It is basically an infeasible path or an unreachable code here, which is detected because of the propagation of the constant and of course, the modeling of the problem as optimistic lattice. So the main thing here again is we started with the first basic block here, and then we had a condition which at the end of that block, which is I greater than 0, and using the SSA edge, we evaluated this condition. That turned out to be the branch is true in the direction. The false direction of the branch is not executed as per the algorithm. That puts in the block of numbers 10 statement here, which is J equal to 10 into the executable path. We went further there and we evaluated that. And then we took the SSA edge of J1 and populated the phi function. You can see that, and then there was jump after this J equal to 10 to this join point, which is J3's things. So the other side, of course, was unreachable because of the branch not evaluating. So it was never put in the work list. But we evaluated his jump and we went straight here into the J3 is equal to phi function of J1 and J2. And using SSA edge of J1 equal to 10, we propagated it there. At this point, we face the lattice because J2 is something which we did not have. And we use the optimistic formulation that it is unknown at this particular point, but it's likely to evaluate it as a constant. We evaluated it as a constant, and that led to the constant propagation of J3 and so on as K. And in fact, in the sense of loop also, this could easily be the case. As you can very well imagine, this could be these branches. So let me just kind of quickly switch to that, and then I'll take some questions. And so that is essentially the sparse conditional constant propagation. But let me just show you a loop-oriented example here, which is okay. The similar example, very similar to what we have seen, easily extrapolatable in the loop sense also, and it's where it really proves to be very, very useful to propagate constants in terms of this type of a flow graph. So here is our block, which is typically our pre-header. And for the sake of simplicity, I'm going to draw our traditional diamond sort of a graph. And here is a back edge here. And here is our constant. Well, this is I0 as 10. And let's say inside this, we have a definition of something like, and this is really a bottom, known bottom, let's say. This could be like a read from some place. So it is a real bottom, known bottom, and very simple here. We have a phi function. We have a phi function here first, and I'm going to call this as, let's say, I2. So, and this one is I3, the real bottom here. So this I2 becomes a part of this from this side, and from this side I1. Sorry about the clutter here. So the bottom things I'm going to rewrite here. I3 is equal to P of I2 and I1. This one over here, I2 is phi of, you can see that I3 and I0. Okay. And then we have a branch here on I. I'm going to call this branch I2 oriented branch. I2 is greater than 20. Okay, obviously this branch is false. And let's say this is the false outcome of this, and that's the true outcome of it. Okay. So now you can see what is going on. So first we'll start here. This is the basic block which will be enabled, and CFG work list will have this, and that will be evaluated top down. And we'll have this I0 as 10. And what we'll do is we'll take the SSA edge here, and we would go ahead and propagate to this phi function the value of I0. So this phi function will look like this, I3. Okay. And this is going to get evaluated to I2. So once we finish the execution of this block now, the SSA edge is enabled, which means the value is propagated. But because of fall through edge, we will put this block into the CFG list, and we'll start evaluating that next. So you can see that the first function we'll face here is this phi function in terms of 10 and I3, and how to evaluate this I2. As per our pessimistic stuff, this I3 were to be bottom, okay, which it would be, because all of them are evaluated as bottoms to begin with, unless they're explicit constants like this. You can see that immediately everything will turn into this I2 will turn into a bottom, and this branch, because it's a bottom times 20, the outcome of this will be a bottom, and it can go both ways. So both blocks will get added to the CFG work list, and we propagate that and blah blah blah. It will reinforce, and the final solution will be that all of the i's that you're seeing here, I2 and then I3 and so on, they will be bottoms. They will converge to this solution. And that's, of course, we want to avoid. And so what we do here in this particular formulation is we will initialize all of the IR statements either as constants or tops. And then not only we'll do that, we'll use optimistic execution or optimistic evaluation. So this I2 will say that, hey, it is getting married between 10 and I3, and it is basically 10 and top. So 10 and top will make an optimistic evaluation to 10. That, hey, 10 and this unknown will turn out to be in our favor. Let's be optimistic, unless otherwise we explicitly prove it. So we'll go with that assumption, and we'll go here, propagate this constant value from the SSA edge to this I2 as 10. Now 10 greater than 20 will be now evaluated to false. You can see what is going on here. We will come here. We'll evaluate this block, which has no definition of I again. And we carefully, therefore, will circumvent the unreachable code here, which has the definition, which is a problematic definition of I1. So once we do that, we'll again go through the fall through edge. The important thing that has happened is this is the edge which was enabled, and this was not enabled to begin with. Now it so turns out that maybe this side of the branch also has I definition, sure, and that happens to be unknown. It will be carried over here. This will evaluate to an unknown. It will be fed, it will turn into a bottom, and that will, in the next round, we will evaluate it. We evaluated along this edge along the first round. We will evaluate it along that edge in the second round by propagating the, because that would enable the execution of this block again, and this bottom will get married to this, in that particular case, to 10, and it will become again a bottom. It will enable this side, and so we would basically converge in a different way. But in this particular case, we can see that we have gone on this path, we have gone on this particular one, and now what we are doing here is we have the other phi function which we still need to get through, which is this one. And the value of I2 here, you can see has what has happened is we had evaluated to be 10. So this is 10. The value of I1, what is it now? Again, in our formulation, it was top. Okay, although we have not evaluated it, the original initialization of lattice is still in place, which is top. Again, optimistic evaluation between a top or an unknown with the 10, and that leads to 10. And this value again flows back here as 10. And that's where you can see that it does not change whatever was, and the particular predicate here, and we terminate here because there is no change in the basic blocks lattices. And when we converge, there's no change, and that's how this formulation takes care of unreachable code in this particular way. Okay. So optimism, initialization of this into a top, and marrying the top with constant is a constant, and then evaluating these basic blocks when they become actually enabled for execution through the control flow. That's the third asset. That leads to now all the I2s and I3s of this as constants, and it also makes this unreachable code, and this block will never get marked here during this particular emulation, and whatever blocks are not really marked, we can get rid of them. So it also leads us to a constant based unreachable code elimination, which is different than obviously whatever we have seen earlier, which is in terms of the deadness is a different problem because it determines if the branch or operations are really needed for a given critical operation. So it will mark differently. That is so the dead code elimination does not cover this case, in short. The other one, which is a purely control flow based unreachable code elimination, because some dangling edges in the graph and there's no path being there, etc., that also doesn't capture this. So, so this is a very powerful optimization in that particular sense. Some unreachable code going along. So that's all I had to say. I'm certainly going to leave the detailed algorithms and to verify that that's how they are really working, which is fairly easy to say by following their flow and the notation there. And but I hope you got the main ideas here, which are about the modeling of the lattice, keeping things in terms of top instead of bottom, and being optimistic, and then finally trying to do propagation of the branch outcomes in between as per the optimistic lattice evaluation. And you can also check that in case things fail, that there are definitions on other paths and all that, they are properly accounted for. And this doesn't lead to something unsafe. That part you can actually check. It's very clear here that on this path, if there was some definition of I, we would use that. And if you run into a real, in short, if you run into a definition point of a variable which is on a currently executing path, which is a bottom, it will be accounted for right away in the next phi function. And from there it will propagate and it will reset things in case it needs to. Okay, any questions? Otherwise, I'd like to at least get started on the global value numbering, and rather value numbering as an optimization. And again, why SSA here? Because of order of n execution here. It's pretty much abstractly interpreting a program, but not going multiple times around the loops. Abstract interpretation or symbolic execution, etc., would have executed multiple times. We don't need that. Here, the execution is in terms of number of edges of the control flow graph. So if we cover, for example, in this case, the top block has 2 edges. If we propagate the information on output edges, then we are sure that the propagation is done. So that's the essence. We don't have to go through this loop 100 times, for example, but in a symbolic execution, we'll have to do that because it's the path condition which can keep changing in terms of symbolic execution. Here, since it is pertinent to constants, it will not change after the constants are stabilized. And the constant stabilization means propagation along all different incoming edges. Whereas, if it is a general path condition, which is x less than a, where neither x nor a are a constant and both are changing, then obviously you cannot make this claim because they are not stable in terms of their values. They could suddenly become constant, could suddenly become non-constant, could become non-constants again. So this claim is not possible to make once unless it's constant. And however, for constants, we are able to catch many more values inside these loops, and so we can speed them up by using this technique. Okay, so let me stop here. Are any questions, clarifications?
Nothing on chat.
Okay, so I suggest you read the Muchnik handout, look at the slides also. Of course, I have gone through them pretty much, but go through the algorithm, step through them, and then answer the questions. And if you have any questions about those, let me take them offline. Now, let's do our next thing here, which is global value numbering, which is a very, very important optimization for our domain here, which is SSA based. And that pretty much subsumes the many of the SSA based optimizations which have been very much the basis for real use of SSA in terms of doing things there. So let me first get that presentation here. And can you see it, Nathan?
Yes, we can.
Okay, so I believe those who did 40 to 40 with in my undergraduate offering, we have of course looked at it. Some others might have done it as well, but the main goal of all these things that we are talking about in terms of redundancy of expressions, copy propagation, constant propagation also to things is unified, is what is called as this value numbering optimization. And it's very powerful to catch all these things. And the modern analysis is, of course, base it on SSA for the reasons, again, the same reasons. It is able to establish this relation or different values in a very quick manner by leveraging the properties of SSA. So what is this value numbering optimization? We should see that first. We'll look at it in a non-SSA sense, and then we'll go into an SSA based version. So main goal here is to track the data flow using something called as a tag number or a value number, what we call it. And we transfer the value number from one variable name to the other name. And then we use these tag numbers or the value numbers to generate the expressions. So we convert from A plus B to the A's value number plus B's value number into that particular representation. So it's a domain transformation into that domain of values. We represent expressions. We assign new values to the synthesized sub-expressions. And we first check if they are there or not already generated, and if they are, and if they are present in particular temporary names. That's how we get rid of the redundant computations. And we, in this particular process, do something else on the fly, which is some algebraic transformation. For example, x times 1 should be same as x, x plus y and y plus x are same. These kinds of things, commutativity. And then we also fold constants, because if we have a value associated with a constant and that value number flows into another variable, from there it flows into its use, we actually say that that particular thing is a constant, and so on. And initially, when this optimization came into being, it was extremely powerful, was well known that it is very good, but was simply applied in the basic blocks because of the amount of time it took to do this on a global basis. Global means within a function call. Later on, it was extended into what we call as superlocal value numbering, which also you have seen in 4240. Which is an extended basic block structure. We go top to bottom from there, and we propagate the value numbers, and the optimization is carried out during that particular basis. There was no SSA then, so this optimization had some many quirky stuff going on with it, which I don't want to confuse with. But I want to first give you a sense of this optimization, and then directly jump into the SSA based things. What was the quirky stuff going on? Because the variable names got redefined. So then what happens to all the value numbers associated with the original definition? What happens to the expressions which hold those values? I mean, there are hundreds of all these kinds of issues which were really as a result of non-clean value to name mapping. And when it became one-on-one, in other words, in the when we generate in SSA sense a unique name for each value, all these issues went away. So here is how I'm going to tell you a little bit about value numbering, and then we'll look at a simple example which I'll work with you, and then we will then look at the how this problem manifests into SSAs and other stuff, things like that. So as I was mentioning earlier, each of the names get a value, a number rather. And then when we form an expression, we will generate a unique value number for the result of that expression. So how do we do that? So we use an expression value tree as a representation here, and we use hash table as a lookup data structure here. So whenever we encounter X, let's say we don't have any value number for it, we keep track of the current names and the assignment of the value numbers. So we'll hash X here, and we'll find out that, hey, no, there is no value number associated with X, neither is with Y, and whenever we encounter first, we'll give some value numbers with them, unique ones, and we'll keep track of them in the hash table, that X has XV as a value number, and Y has YV as the value number. And now what we'll do is we will have these expressions as we'll encounter, and we will try to walk the IR again in the lexical sense from top to bottom, And we'll take the right hand side, which will be typically an expression like, for example, x plus y kind of stuff. And we will hash each one of the names and find out its value number, and we'll generate a value tree out of it. And then we'll look up the value tree in the hash table. If it's not there, we'll insert it. We'll give it a new number because it's a synthesized value. And if that has an left-hand side to it, suppose t is equal to x plus y, we'll give that value number to that t. And sometimes we'll not have this particular explicit temporary assignment, such as, it's a part of if expression, for example, if x plus y is less than 10, something like a predicate. So there is no temporary there, depending on the IR cogeneration level types. So in that particular case, we'll assign a temporary name to it, assign a value number of this expression, and we'll put this instruction to at the right place so as to explicitly note the value associated with that sub-expression. The reason is this, that we need to have an L value as a named entity to pick up the value of the right-hand side to be able to do the optimization. Because if we find that it's already available, this value is available in some name, then we can simply use that name, as it will become clear through some simple example. And so if it is found that there's value number already there, expression, we'll look up its reference to the variable, which is an L value, and there could be several one of them, and we'll pick up one of them, and instead of that sub-expression, we'll use that variable. And that's how we would have eliminated a redundancy, because instead of recomputing in short, instead of recomputing the value at the given point, we have actually found it already there in some variable name, and that's the way the redundancy is eliminated. And interestingly, it is not just a lexical issue, but as you will see, it will be very interesting to allows us to do this across different variable names as well. So with this, keep this algorithm in your mind. Again, it's very simple. Whenever a name is encountered, we'll first find out if there's a value number with it. It's not there, we'll assign it a value number. First step. Second, whenever we have a value number associated and we have a sub-expression, we'll take those value numbers of its components, we'll generate a value tree, we'll hash it, and we'll find out its value number. If it's there associated with the value tree is already present in and encountered, and a number with it, if we find it through hash map, okay, then we'll use that value tree's number, and we'll go to the respective variable which is holding that particular value tree's number, and then we'll simply substitute that variable over here at the current point. If we don't find it, of course, we'll generate a new one and we'll assign it to the left-hand side variable, and we'll keep going on and on and on. And to just align the expressions algebraically and so on, we'll treat x times 1, x plus y, same as y plus x, all these kinds of transforms we'll worry about. And in this particular process, if we find some values are bound to some constants, and those values, there is a use of those variables in some places, we'll also find that out if there is a use of the constant values, and if they are there, then we'll simply forward the instead of recomputing these or reassigning these constants and things like that, we'll simply use the temporary over there to propagate the constant values. Okay, so with that, let's look at it in a little different way, which is a simple example. Okay, so the essence of this, I'm going to give you a very simple example. Okay, this is my favorite example. And we can, of course, add some more stuff to it, but let's start here. So what we'll do here is we'll maintain a table, which is a value table for each one of the names, and whether there is a value number associated with that or not. So this is the way it will look. And if it's again a hash table implementation. So this is about the names, and the other one will be about the expressions. So I'll start with the names. So first we'll go to the R value side here, and we'll be processing all this, by the way, top down, and this is just within a basic block. So we'll look up A here, as you can see, find out in this hash table the variable name and the value. This name is not found, obviously, so we need to assign a value number. We'll install it here, and we'll give it a value number 1. Just very simple. I'm trying to keep it really simple here. And then this is the expression itself right now on the first statement. So nothing further is to be done. Next, what we'll do is we'll come to the left-hand side of this, and our goal is to process this assignment statement. So whatever sub-expression we have, its value number is to be transferred to this P. Okay, so this P will be in the symbol table, in the value table. It could be already there, by the way, but we need to update its value number because at this particular point, P is equal to A is processed. So we'll update it to P is equal to 1. If it's not there, we'll also, of course, install it and give it the name number of A. Now we'll come to the second statement and do the same thing there. B is not there, and we'll look up the value number. It's not there. B, we will give it a value number 2. In this case, very simple, tag. And this Q, even if it's there, we'll update it to 2. Okay, so far we have processed both of these statements. Now we come to an interesting statement. T1 is equal to P plus Q. And what's going on here is we'll again look up P. In this case, obviously it is there in the hash table, and it has a value number associated with it. If it were not there, we will install it and give it a new value number, but in this case it's already there. And so our goal will be to construct a value expression here from the IR expression. So for that matter, we'll take the operator and we'll take the first operand, find out if its value number is there or not. In this case, it's there. In other case, if it's not there, we'll install it first and pick up that value number and put it here. So in this case, it will be just 1. And Q is also to be looked up here. So this is the plus 1, 2 will be the expression that will be in the value expression side. Now this expression is kept, okay, in another table here. which is this expression E. I'm just calling this E here. So you can imagine this E here and a value number associated with that. So far, when we look it up, this particular expression in this table, it isn't there. So which means we are encountering it the first time. Remember, in this particular process, we would have done the commutativity and all these other issues there. So if there was some other expression earlier, Q plus P, it would be found with that value number over here. But in this particular case, it is encountered first time. And so we will put this expression E1 here, whatever this, and which is this expression, which we'll be using a hash map for locating it. And we'll give it some value number, let's say 3, because it's the first time it's getting in there. Once we finish that, so we would have done this side and given it an expression value number 3. The next goal will be to again process the LHS of this left-hand side, which is our temporary T1. And what we'll do is we'll take this temporary T1, assign a value number 3 with it, okay, coming out of that expression. So we're done with this third statement. Now we are at the fourth statement, and this is where very interesting things take place, as you can see. So again, we'll process A plus B. How do we do it? Again, look up A, and if it's not there, install it in the value table of variables. If it's there, take its value number and try to construct its value tree. So this plus, then A is there, it's 1. And then B is also similarly found here as 2. So this is found, both of A and B are found in the value table as plus 1, 2. And this is how we constructed A plus B's expression here, E2. Now you can see that we'll again do a hash map check on this over here. And that value expression plus 1 true is now found in the expression table. And that basically means that this expression was computed and its value number is 3 and so on. So we'll see. And in this particular case, we'll see that can we actually find this value in a named entity? We'll do a lookup using this value on this table. So this was found here as T1. So we'll take that T1 as a named entity, and this one will become T1. And this T1 is value number is now transferred to T2. So T2 will also be named as 3 here. And at that point, we are completely done. So you can see that in this process, what we have done is we have picked up a redundancy between P plus Q and A plus B because both of them carried the same expression value tree, which is plus 1, 2. Why? Because you can see P was a copy of A, Q was a copy of B. So P plus Q and A plus B pretty much have the, or actually have the exact same value all the time. And this was picked up by the value numbering. In original CSE or PRE or all these formulations, you could see that you would not be able to do so. This the power of value numbering. We would be able to do so if we had done some copy propagation and so on, and canonicalize these expressions and things like that. And that's how we would be able to do it, or done some constant propagation, which is yet another case wherein the value numbers are going to become the same. So this happens to this lexically disjoint expressions carry the same value numbers if they're derived from copies or they're derived from constants. And you can easily see that this particular relationship keeps growing transitively. In other words, imagine two values, and this is completely independent of this particular example. I'm considering T1 and T2, two values, to determine if they're identical in terms of values. Now, they might be derived from some variables A and B. This might be from C and D. And this A in turn could be derived from some other variables. This B could be derived from some other, C could be derived, and so on. If the way the A is generated and C is generated is identical, and B is generated and D is generated is identical in some sense, then these two would probably be identical too. And in general, this keeps this particular congruence, or what I call it as the fact that T1 and T2 are identical depends on A's constituents, B's constituents, C's constituents should be same as A's constituents, and B's constituents should be same as D's constituents. And transitively, it can keep happening further and further, means that simply doing some constant propagation and some copy propagation might be the very shallow and one level of effort that may be needed to expose the redundancy between P plus Q and A plus B. For this example, it's sufficient. But in general, it may not be sufficient at one level. You may have to iterate it hundreds of times to really fully capture this. So the question is, again, iteration is not something which is helpful to us time-wise. SSA-wise, can we capture this using this type of representation that A is derived using such values, B is derived using such values, C is derived using such values, and D is derived using such value? Come up with a SSA-based algorithm to determine if T1 is equivalent to T2. So is this possible? The answer to that is it is very much possible in SSA because of, again, very fast navigation of which value is derived from where and how they get merged and so on in a single assignment side. And that's why for solving this problem in general across basic blocks and so on, what we call as a global value numbering, which is very much similar to this type of value numbering that we do, but by using SSA and by using these kind of trees, what we call as value trees, is much, much faster. So that is the topic which we'll cover using SSA, how to build these value trees and how to determine their equivalence and therefore do optimization by using them is what is covered further in the slides. In between slides, please ignore because they will be confusing to you. We are not going to do value numbering based on the traditional namespace. We will be in the SSA namespace because of that's where the efficiency is in terms of, again, here you can see that in order to determine T1 and T2's equivalence, we have to go to the constituents of them, and again from there, their constituents and so on. And we have to pretty much, in the worst case, cover the whole program space in terms of how values are synthesized, how they get propagated from one to the other, which is exactly the same as the SSA-based propagation of these values. And so SSA allows very efficient propagation of values to determine their equivalence, in short, and that's why SSA. All right, thank you. So let me stop here and we'll have office hours now. And see you next week. Thank you. If you have any questions, come over to the office hours. Otherwise, please go ahead and do the homework for both the questions and you can read the respective parts and get it done. Thank you and see you next week.